July 1st, 2025, 23:47 UTC, Rio Hurtado, Chile. A computer screen flickers in the darkness. An automated telescope operated by the Atlas survey scans the southern sky. It's a routine night, the same routine that happens every clear night. Point, capture, process, move on. The system is designed to find asteroids that might threaten Earth, rocks from our own solar system. Nothing exotic, nothing special. Then a number changes. An algorithm flags something. A faint point of light moving against the background stars. Too fast. The trajectory doesn't fit. The computer calculates the orbit. Once, twice, 3 times. And then the system does something it's only done twice before in human history. It sends an alert marked with a single word: Interstellar. For the 3rd time ever, we've detected something from beyond our solar system. Something that traveled through the void between stars. Something that formed around a sun we've never seen. Its name, 3I Atlas. And what scientists are discovering about this cosmic traveler is rewriting everything we thought we knew about how other solar systems form. Because this visitor from another star, it shouldn't exist. Not with the chemistry it carries, not with the behavior it's displaying, not with the story it's telling about a place so far away that light itself takes millennia to cross the distance. This is the story of 3I Atlas, the interstellar comet that came from somewhere beyond imagination, that appeared in our skies for just a few brief months, and that's forcing us to confront a humbling truth. Our solar system might be the exception, not the rule. The hunt for interstellar objects didn't begin in 2025. It began decades ago with a simple question that seemed almost philosophical. Are we alone out here? Not in terms of life, though that question matters too, but in terms of stuff. Does the space between stars contain wandering debris, rocky fragments, icy bodies? Or is the interstellar void truly empty, with each star system keeping its material contained by gravity's invisible fence? For most of human history, the answer seemed obvious. The space between stars is vast beyond comprehension. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. That's 40 trillion kilometers, 25 trillion miles. A distance so enormous that Voyager 1, the fastest spacecraft humanity has ever launched, would take 75,000 years to reach it. Surely nothing crosses those distances. Surely each star system is its own isolated island. But astronomers knew better. They understood orbital mechanics. They understood that during planetary formation, chaos reigns. Young planets gravitationally scatter material in every direction. Some debris falls into the star, some forms moons, and some, maybe 1% or less, gets flung outward with enough velocity to escape the star's gravity entirely. Ejected, cast out into interstellar space, traveling forever, or at least until it encounters another star system millions of years later. The mathematics suggested these interstellar objects should exist, billions of them drifting through the galaxy. Fragments of destroyed worlds, pieces of failed planets, comets that never found a home. But detecting them, that was the problem. They're small, they're dark, they move fast, typically 20 to 30 kilometers per second relative to our Sun. By the time you spot one, it's already leaving. And unless its trajectory happens to carry it close to Earth, you'll never see it at all. Then came October 19th, 2017. The Pan-STARRS. One telescope in Hawaii detected something strange, an object moving through the inner solar system, already past the Sun, already heading back into deep space. Its orbit was hyperbolic. not elliptical like comets and asteroids from our system, hyperbolic, which meant it came from somewhere else. It was designated ʻOumuamua, the first, the scout, the messenger. ʻOumuamua was bizarre. It was shaped like a cigar, or maybe a pancake, nobody could agree. It tumbled chaotically through space. It showed no signs of cometary activity, no tail, no coma. Yet it accelerated slightly as it moved away from the sun, pushed by some force nobody could initially explain. Harvard astronomer Avi Loeb famously suggested it might be artificial, a light sail from another civilization. Most scientists disagreed, proposing it was a comet releasing gases we couldn't detect. But everyone agreed on one thing: Oumuamua was weird. Then came August 30th, 2019. Amateur astronomer Gennady Borisov, using a homemade telescope in Crimea, spotted another interstellar visitor, 2I/Borisov. This one looked normal. It had a coma. It had a tail. It released carbon monoxide and water vapor exactly like comets from our own solar system. Scientists breathed a collective sigh of relief. Interstellar comets were just comets, nothing exotic, nothing inexplicable. Oumuamua was the outlier. Borisov was the norm. Or so they thought. Until July 1st, 2025. Until 3I Atlas appeared, and until the data started coming in. The discovery itself was almost accidental. The Atlas system, short for Asteroid Terrestrial-impact Last Alert System, scans the sky looking for near-Earth objects, rocks that might hit us. It's a planetary defense system, not an interstellar object hunter. But on that July night, its cameras captured something moving through the constellation Ophiuchus. The initial observations were unremarkable. Faint object, maybe magnitude 19, barely visible even to large telescopes. But within hours, other observatories confirmed the sighting. The Zwicky Transient Facility in California, the Canada-France-Hawaii Telescope, the Lowell Discovery Telescope in Arizona, and every one of them calculated the same troubling orbit. Hyperbolic, extremely hyperbolic, with an eccentricity of 1.0004, meaning it was moving far too fast to be gravitationally bound to our Sun. On July 2nd, 2025, the Minor Planet Center made it official. The object received an interstellar designation, 3I Atlas, the third confirmed visitor from beyond our solar system. Within 24 hours, every major telescope on Earth turned toward it, because this was a chance that comes maybe once a decade, a chance to study material from another star system, a chance to answer questions about planetary formation that can only be answered by looking at examples beyond our own backyard. But nobody expected what they found. The first hint came from spectroscopy. When you split light from a comet into its component wavelengths, you see the chemical fingerprints of whatever gases are escaping from its surface. Every molecule absorbs and emits light at specific frequencies. Water has a signature. Carbon dioxide has a signature. Carbon monoxide, cyanide, methane, they all have signatures. By analyzing a comet's spectrum, you can determine its composition without ever touching it. On August 6, 2025, the James Webb Space Telescope pointed its near-infrared spectrograph at 3I Atlas, the most powerful space telescope ever built, designed to see the first galaxies formed after the Big Bang, turned its attention to a tiny comet that had traveled across light years to visit us. The spectrum came back within hours, and scientists stared at the data in confusion, because the numbers didn't make sense. 3I Atlas was releasing carbon dioxide, lots of carbon dioxide, An 8-to-1 ratio of carbon dioxide to water. That's not just unusual, that's extreme. Most comets in our solar system are dominated by water ice. Water makes up 70% to 80% of their composition. Carbon dioxide is present, sure, but in small amounts, a few percent at most. But 3I Atlas, it was flipped. Carbon dioxide dominated. Water was the minority component. Jacqueline McCleary, an astrophysicist at Northeastern University, described it perfectly. The ratio was literally out of this world. She's right. It's among the highest CO2 to water ratios ever measured in a comet. And it raised an immediate question. Where did this thing form? What kind of environment produces a comet made mostly of dry ice instead of water ice? The answer lies in temperature. Water ice forms when temperatures drop below 273 Kelvin, 0 degrees Celsius, 32 degrees Fahrenheit. That's cold by Earth standards, but relatively warm in cosmic terms. In a protoplanetary disk, the swirling cloud of gas and dust that surrounds a young star, water ice forms relatively close to the star, within a few astronomical units, the region where rocky planets like Earth typically form. Carbon dioxide ice, though, that requires much colder temperatures, below 194 Kelvin, minus 79 Celsius, minus 110 Fahrenheit. In our solar system, CO2 ice only forms in the outer reaches, beyond the orbit of Neptune, in the Kuiper belt, in the Oort cloud. Regions so far from the sun that sunlight is a distant memory. If 3I Atlas is rich in carbon dioxide and poor in water, it must have formed in the frozen outer regions of its parent star system, far from the warmth, far from the light, in a place where temperatures never rose high enough for water ice to be the dominant material. But that's not the only explanation. There's another possibility, one that complicates the story. Maybe 3I Atlas didn't form that way. Maybe it started as a normal comet, rich in water ice, but something happened during its journey through interstellar space. Radiation from cosmic rays, impacts from interstellar dust, chemical reactions occurring over millions of years. Perhaps the surface water sublimated away, molecule by molecule, leaving behind a carbon dioxide-rich shell. Scientists call this the protective layer hypothesis. Imagine a comet traveling through the void for 10 million years, maybe 100 million years, exposed to galactic cosmic rays powerful enough to break chemical bonds. The outer layers would be altered, water molecules would be destroyed or driven off. More durable compounds, carbon dioxide, carbon monoxide, complex organics, would remain. By the time the comet enters another star system, its surface composition no longer reflects its original bulk composition. It's been weathered by interstellar space itself. Which theory is correct? Scientists don't know yet, but the implications are enormous. If 3I Atlas's composition reflects its formation environment, it tells us that some star systems have protoplanetary disks much colder than ours. That planet formation can occur under conditions drastically different from what we observe around our sun. If the protective layer hypothesis is correct, it tells us that interstellar space is not empty and benign, that travel between stars actively alters objects, that the journey matters as much as the origin. Either way, 3I Atlas is teaching us something fundamental. Our solar system might be unusual. The comets we've studied for centuries, Halley's Comet, Hale-Bopp, Hyakutake, might not represent the cosmic norm. They're just the ones that happen to share our neighborhood. But out there, orbiting other stars, forming in different temperatures under different conditions, comets might be vastly more diverse than we ever imagined. The size of 3I Atlas added another layer to the mystery. Initial estimates suggested the nucleus, the solid core beneath the gas and dust, was somewhere between 320 meters and 5.6 kilometers in diameter, most likely less than 1 kilometer. That made it similar in size to 2I/Borisov, the previous interstellar comet, and possibly comparable to ʻOumuamua, small by comet standards, not a giant like Hale-Bopp or Comet Siding Spring, but still substantial, a kilometer-wide chunk of ice and rock traveling at 68 kilometers per second relative to the Sun. But here's where things got interesting. The coma, the cloud of gas and dust surrounding the nucleus, was huge. Images from NASA's Spherix Space Telescope revealed a coma spanning 26,400 by 24,700 kilometers, nearly twice the diameter of Earth. That's enormous for a nucleus less than 1 kilometer across. It meant 3I Atlas was actively releasing material, lots of material, and it had been doing so for a long time. NASA's Transiting Exoplanet Survey satellite, TESS, captured pre-discovery images dating back to May 7, 2025, when the comet was 6.4 astronomical units from the Sun, roughly the distance of Jupiter. That's twice as far as the asteroid belt. At that distance, sunlight is weak, temperatures are frigid, yet 3I Atlas was already active, already releasing gases, already developing a coma. That early activity confirmed the carbon dioxide dominance. Water ice doesn't sublimate at those distances and temperatures. It remains frozen, inert, waiting for the warmth of the inner solar system to awaken it. But carbon dioxide ice, it sublimates at much lower temperatures. Even at 6 astronomical units, even in the dim chill beyond Mars, CO2 ice begins to turn directly from solid to gas. The fact that 3I Atlas was active so far from the Sun proved it had to be rich in volatile materials. Materials that respond to even faint sunlight. Materials like carbon dioxide. As 3I Atlas traveled inward, its activity increased. The coma grew larger. The tail became visible. By mid-July, amateur astronomers with modest telescopes could photograph it. By August, the coma had turned reddish, a color indicative of dust. By September, during a total lunar eclipse, when the sky was exceptionally dark, astrophotographers captured images showing the comet glowing green. That green fluorescence comes from diatomic carbon, molecular fragments created when sunlight breaks apart larger organic compounds in the coma. It's a common feature in comets, a sign of active chemistry occurring in the gas cloud surrounding the nucleus. But the real show was yet to come, because in late October 2025, 3I Atlas would reach perihelion, its closest approach to the Sun, and that's when everything would happen at once. Perihelion is the moment of truth for comets. It's when they pass nearest to the star, when solar radiation is most intense, when surface temperatures soar, when ices sublimate at maximum rates. For comets from our own solar system, perihelion is often spectacular, brightening by factors of 10 or 100, developing tails that stretch across the sky, sometimes fragmenting under the stress, sometimes evaporating entirely if they pass too close. For 3I Atlas perihelion would occur on October 29, 2025, at a distance of 1.36 astronomical units from the Sun, just inside the orbit of Mars. Not dangerously close, but close enough to heat the surface significantly, close enough to trigger intense outgassing, close enough to reveal what this interstellar visitor was truly made of. Observatories around the world prepared. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter, both in orbit around Mars, plan to photograph the comet as it passed. They're designed to study the Martian surface, not distant comets, but the opportunity was too good to miss. High-resolution cameras, spectrometers capable of analyzing the comet's composition, a vantage point unavailable from Earth. On October 3rd, 2025, when 3 IE Atlas passed within 30 million kilometers of Mars, both spacecraft executed their observation sequences. The images came back within days. They showed exactly what astronomers expected: a bright nucleus surrounded by a diffuse coma, a faint tail streaming away from the sun. Nothing obviously anomalous, nothing that couldn't be explained by standard cometary physics. But the spectroscopic data, that was more interesting. The Very Large Telescope in Chile had already detected cyanide and nickel in the coma. Both compounds are found in solar system comets, but nickel is unusual. It requires high temperatures to form, typically in the interiors of stars or during supernovae. Finding it in a comet suggests the original protoplanetary disk contained material from previous generations of stars. Material forged in nuclear furnaces, scattered by stellar explosions, then incorporated into the disk that eventually formed planets and comets. The nickel detection gave scientists a clue about 3 I Atlas's origin. Not a specific star that would be impossible to determine, but a general region of the galaxy. Analysis by Yang Guo and collaborators suggested the comet might have passed within 3.3 light-years of 25 known stars in the past 10 million years. It could have originated from any of them, or from a star that no longer exists, having exhausted its fuel and collapsed into a white dwarf or neutron star billions of years ago. The comet might be older than its parent star's current state, a relic from an era when that star was young, surrounded by a disk of forming planets, violent and chaotic and full of possibility. Some scientists propose the comet came from the Milky Way's thick disk, a population of older stars with lower metallicity than our Sun. If true, 3 I Atlas's parent star would have had a heavy element abundance of at least 40% of the Sun's. That means fewer rocky materials, less iron, less silicon, a star system where the conditions for planet formation were subtly different from ours, where the chemistry skewed toward volatiles, where comets might naturally be richer in carbon compounds and poorer in water. But perihelion passed. The comet survived intact. No fragmentation, no sudden brightening indicating a catastrophic breakup. It simply continued on its trajectory, outbound now, heading back toward interstellar space. And that's when the real race began, because after perihelion, 3 I Atlas would make a series of close approaches to planets in our solar system. Each one offered a chance for observation, each one a window into the comet's behavior and composition, each one potentially the last good look before it faded from view forever. On November the 3rd, 2025, the comet passed within 97 million kilometers of Venus. On December 19th, it would make its closest approach to Earth, 269 million kilometers. Still distant, no threat of impact, but close enough for detailed observations from ground-based telescopes. The Hubble Space Telescope, the James Webb Space Telescope, the Very Large Telescope in Chile, all would be tracking it, all gathering data on its nucleus, its coma, its tail, all trying to squeeze every last bit of information from this fleeting visitor before it disappears. Then, in March 2026, comes the final opportunity. The comet will pass 54 million kilometers from Jupiter, and NASA's Juno spacecraft currently in orbit around the gas giant might be able to observe it. Not with its main camera, that's designed for photographing Jupiter's clouds, but with its other instruments: spectrometers, magnetometers, particle detectors. If Juno can capture data on 3I Atlas after perihelion, after the comet has lost much of its carbon dioxide ice, scientists might finally see what lies beneath: the rocky core, the primordial material, the truth about where this object came from and what it's made of. But that observation depends on mission controllers choosing to dedicate precious spacecraft time to a target that wasn't part of the original mission plan. It depends on whether the comet is still bright enough to detect from Jupiter's distance. It depends on 100 technical factors that won't be decided until the moment arrives. And by then, 3I Atlas will already be on its way out of the solar system, moving at 68 kilometers per second, never to return. Within a year or two, it will fade below the detection threshold of Earth's most powerful telescopes. Within 5 years, it will be hundreds of astronomical units away, deep in the outer solar system, where only the sun's faintest whisper of gravity can be felt. Within a few decades, it will cross the heliopause, the boundary where solar wind gives way to interstellar medium, and then it will be gone, back into the void, traveling toward another encounter with another star millions of years in the future, carrying with it whatever secrets we failed to extract during its brief passage through our neighborhood. The story of 3I Atlas is not just about one comet. It's about what that comet represents: a messenger from another world, a sample of material formed under conditions we can never directly observe, a piece of evidence in the grand puzzle of how planetary systems form, how stars create the building blocks of worlds, how matter organizes itself from chaos into order. Every planetary system begins the same way. A cloud of gas and dust collapses under its own gravity. The center heats up, igniting nuclear fusion, becoming a star. The remaining material flattens into a disk, swirling and churning, particles colliding and sticking together. Dust grains become pebbles. Pebbles become boulders. Boulders become planetesimals. Planetesimals become planets. It's a process astronomers understand in broad strokes, but the details, those depend on conditions in the disk: temperature, density, chemical composition. And those conditions vary from star to star. In our solar system, the frost line, the distance where temperatures drop low enough for water ice to form, sits around 3 to 5 astronomical units from the sun. Inside the frost line, you get rocky planets like Earth. Outside, you get gas giants and icy bodies. Comets from our system form beyond the frost line, incorporating water ice as a major component. But in another system, with a dimmer star or a different disk density, the frost line might be closer or farther. Temperatures might be colder overall. Water ice might be less abundant. Carbon dioxide might dominate instead. That's the lesson 3I Atlas teaches, that our understanding of planet formation is built on a sample size of 1, our solar system, the planets we've studied up close, the comets we've observed, the asteroids we've measured. But the universe contains hundreds of billions of stars, trillions of planetary systems. Each one is potentially different, each one formed under unique conditions. And until we can sample materials from those systems, study their chemistry, analyze their composition, we can't know how typical or atypical our own cosmic neighborhood truly is. Interstellar objects are the only way to get those samples. We can't send spacecraft to other stars, not with current technology. The nearest star would take tens of thousands of years to reach. But interstellar objects come to us, ejected from their home systems, wandering the galaxy, occasionally passing through ours. Each one carries information. Each one is a data point. With 3 confirmed interstellar visitors, ʻOumuamua, 2 I/Borisov, and now 3 Atlas, we're beginning to see the diversity. And it's stunning. ʻOumuamua was small, elongated, tumbling, with no visible outgassing, yet somehow accelerating away from the sun. 2 I/Borisov was larger, with a normal water-rich coma, behaving exactly like comets from our system. 3I Atlas is carbon dioxide rich, active at great distances, chemically extreme. 3 objects, 3 completely different profiles. If that's representative of the broader population, and there's no reason to think it isn't, then interstellar objects are wildly diverse, more diverse than objects from our own system. And we're about to find a lot more of them. The Vera C. Rubin Observatory in Chile began operations in 2025. It's designed to survey the entire visible sky every few nights, creating a continuous movie of the cosmos. Asteroids, comets, supernovae, anything that moves or changes will be detected automatically. Current estimates suggest the Rubin Observatory will discover 1 or 2 interstellar objects per year, maybe more. Within a decade, we might have dozens of examples. Within a generation, hundreds. Each one will be an opportunity, a chance to study material from another star system, a chance to test theories about planet formation against real data from diverse environments, a chance to refine our understanding of how common or rare different chemical compositions are, and eventually a chance to trace those objects back to their origins. Not definitively, the uncertainties are too large for that, but statistically, to determine which regions of the galaxy produce carbon dioxide-rich comets versus water-rich comets, to map the chemical diversity of the Milky Way, to understand how our galactic neighborhood varies from place to place. But 3I Atlas is more than a scientific curiosity. It's a reminder of our cosmic context. We live on a planet orbiting an ordinary star in an ordinary galaxy. There's nothing special about our location, nothing unique about our solar system except that it produced us. And if our system can eject material into interstellar space, and it does, we know that from studying long-period comets with extremely eccentric orbits, then so can every other system. The galaxy is full of wandering debris, fragments of worlds that never were, pieces of planets that formed and then were destroyed, comets cast out by gravitational encounters, all of it drifting through the void, occasionally crossing paths, creating the intricate web of matter that connects every star to every other star over cosmic timescales. 3I Atlas came from somewhere. It formed in a disk around a star we've never seen. It was ejected, violently or gently, into interstellar space. It traveled for millions of years through the cold and dark. It passed near other stars, maybe close enough for their gravity to alter its course. It survived impacts from interstellar dust. It endured radiation from cosmic rays, and eventually, by chance, its trajectory carried it into our solar system, into our instruments, into our telescopes, into our awareness. For a few brief months, we had the chance to study it, to measure its composition, to calculate its orbit, to photograph its tail, to speculate about its origin. And then it left, as all interstellar objects do, onto the next star system, onto the next encounter, carrying with it the memory of a young star, a forming planetary system, a place and time now lost to history. December 19th, 2025, the night of closest approach to Earth. Across the world, telescopes turn skyward. Professional observatories, university facilities, amateur astronomers with backyard setups, all of them tracking the same target, a faint smudge of light moving slowly against the background stars. Magnitude 10 or 11 by now, too dim for naked eye visibility, but easily captured by moderate-sized telescopes. The James Webb Space Telescope executes its observation sequence, spectroscopy across the infrared band, measuring the gases escaping from the nucleus, tracking how composition changes as the comet moves farther from the Sun. The data will take weeks to fully analyze, but preliminary results come quickly. Carbon dioxide still dominates, but is weakening. The ice is sublimating away. By the time 3I Atlas reaches Jupiter in March, much of the CO2 will be gone. What remains will be the refractory materials, the rocky core, the dust, the compounds that can't be driven off by sunlight alone. Hubble captures high-resolution images of the nucleus. Resolution isn't perfect, the comet is still too far for that, but good enough to see that the nucleus appears intact, not fragmented, not disintegrating, just a solid, slowly rotating body shedding material as it travels. The rotation period is measured at approximately 8 hours, fast but not unusually so for a comet this size. The Very Large Telescope in Chile adds more spectroscopic data, confirming the presence of carbon monoxide, detecting water vapor, present but in small amounts compared to the CO2, finding traces of complex organic molecules, the carbon-based compounds that give comets their reddish color and might have delivered the building blocks of life to Earth billions of years ago. And then, gradually, the observations taper off. The comet continues its journey. December becomes January. January becomes February. The distance increases. The brightness fades. By late February, only the largest telescopes can track it. By March, it's magnitude 15, barely visible even to professional facilities. And then it's gone, swallowed by distance and darkness, receding into the vast empty spaces between stars. The data remains, thousands of images, hundreds of spectra, measurements of brightness, color, activity level, composition. All of it was archived, all of it available to researchers for years to come. The analysis will continue long after the comet itself has faded from view. Papers will be published, conferences will debate interpretations, graduate students will write dissertations, and slowly, gradually, the story of three truths, I, Atlas, will be refined. From a collection of raw observations into a coherent narrative about where this object came from, what it's made of, and what it tells us about the universe beyond our solar system. But one truth is already clear. 3. I Atlas is not like comets from our own system. Its chemistry is extreme. Its behavior is unusual. Its origin is shrouded in mystery. It came from somewhere out there, from conditions we don't fully understand, carrying a message written in the language of molecules and ice. A message that tells us our solar system is just one example among countless others, that the processes we've observed here are not universal, that diversity, not uniformity, is the cosmic norm. And the message is this: we are not special. Our sun is ordinary. Our planets are typical. Our comets are just comets, shaped by the specific conditions of our specific system. But out there, orbiting other stars, forming under different temperatures and different pressures and different chemical abundances, other solar systems are producing objects we've never imagined. Comets made of dry ice instead of water ice. Worlds where carbon dioxide rains from the sky. Planets where the frost line sits so close to the star that even rocky worlds are coated in volatile ices. The universe is stranger than we thought, more diverse, more complex, and we're only beginning to see it. 3 interstellar objects, 3 glimpses of what lies beyond, and each one different from the last. ʻOumuamua, the mysterious tumbling cigar that sparked debates about alien technology and taught us that we don't understand everything we see. 2I/Borisov, the reassuringly normal comet that proved interstellar objects can look just like objects from our own system. And now 3I/Atlas, the carbon dioxide-rich visitor that's rewriting the textbooks on comet composition. What will the fourth interstellar object show us? And the fifth? And the 10th? Will we find a pattern? Or will each one be unique, reflecting the specific conditions of its birthplace? We don't know. We can't know until we see them. But this much is certain. The era of interstellar astronomy has begun. For centuries, we studied only objects from our own solar system. Now, we're studying samples from across the galaxy, messengers from distant stars, time capsules from the ancient past. And with each new discovery, with each new data point, we're learning that the universe is both more familiar and more alien than we ever imagined. 3I/Atlas will not return. It's gone forever, bound for the deep black between stars. But his legacy remains. In the data, in the questions it raised, in the realization that our cosmic neighborhood is just one small corner of a vast and varied galaxy. And somewhere out there right now, another interstellar visitor is on its way. Maybe we'll detect it next year, maybe in 10 years. Maybe it's already inside our solar system, too dim to see, waiting for sunlight to wake it from its frozen slumber and reveal its presence to our telescopes. When it comes, we'll be ready. We'll point every instrument we have at it. We'll measure its composition. We'll calculate its orbit. We'll photograph its tail. And we'll add one more piece to the puzzle of understanding how the universe works, how stars form, how planets coalesce, how life's building blocks are scattered across light years of empty space. This is the story of 3I/Atlas, the interstellar comet that came from beyond, that traveled across distances we can barely comprehend, that spent a few brief months in our sky, and that taught us, once again, that the cosmos is full of surprises, full of wonders, full of objects and phenomena we're only beginning to understand. The visitor has passed, the data remains, and the questions it raised will occupy scientists for years to come. Where did it come from? What conditions produce such an unusual chemistry? Are carbon dioxide-rich comets common in other systems? Or is 3I/Atlas an outlier, even among interstellar objects? We don't have all the answers. Not yet. But we're learning. Slowly. Patiently. One interstellar visitor at a time. And each one brings us closer to understanding our place in the universe. Not as the center of creation, not as the pinnacle of cosmic evolution, but as one small example among billions. One solar system in a galaxy full of them. One planet orbiting one star in a universe full of stars. 3I/Atlas reminded us of that truth, and for that, we should be grateful. Not for the answers it provided, though those are valuable, but for the questions it raised. Because the best discoveries don't solve mysteries. They reveal how much we still don't know. And in that revelation, they give us reason to keep looking, keep searching, keep pointing our telescopes at the sky and waiting for the next visitor to arrive. The cosmos is vast, patient, indifferent, but endlessly fascinating. And somewhere out there, beyond the reach of our instruments, beyond the edge of our solar system, another messenger is making its way toward us. Another fragment of a distant world. Another traveler from the dark between stars. When it arrives, we'll be watching. Because that's what we do. That's what curiosity demands. That's what makes us human. The need to know. the drive to understand, the refusal to accept ignorance when knowledge is within reach. 3i Atlas has left us, but the story it began continues, and it will continue long after we're gone, long after our civilization has faded into cosmic history. The interstellar visitors will keep coming. The galaxy will keep producing them, and maybe millions of years from now, another civilization around another star will detect a strange object passing through their system. An interstellar visitor rich in water ice instead of carbon dioxide. Chemically unusual for their system, an outlier, an anomaly. And maybe they'll study it with their telescopes and their instruments and their curiosity, never knowing that it came from here, from our sun, from the solar system that produced Earth and humanity, and all the dreams we carried into the void. Because that's the other side of this story. We send messengers too. Every long-period comet with enough velocity to escape the sun's gravity eventually leaves. Every object ejected by Jupiter's gravity during its formation. Every asteroid kicked out of the inner solar system by close encounters with planets. They all become interstellar travelers. They all carry samples of our solar system into the galaxy. And over billions of years, those fragments will visit thousands of other star systems. They'll pass near other planets. They'll be observed by other astronomers, if those astronomers exist. They'll tell the story of where they came from. What will they say about us? About the system that produced them? They'll speak in the language of chemistry, water ice and silicate rock, ammonia and methane, complex organic molecules formed in the cold reaches of the outer solar system. They'll tell a story of a G-type star of moderate size, a planetary system with 4 rocky inner worlds and 4 gas giants farther out, a frost line around 3 astronomical units where water ice becomes stable, a history of violent collisions that shaped the planets into their current configurations, the late heavy bombardment that scarred the moon and possibly delivered water to Earth. All of it recorded in the composition and structure of the debris we eject. Someday, an astronomer on a distant world will study one of our cast-off comets. They'll measure its chemistry. They'll marvel at its water richness. They'll wonder what kind of star system produces objects like this. And if they're very thorough, if they're very lucky, they might trace its trajectory backward through space and identify our sun as the origin point. They might point their telescopes at this yellow star, this unremarkable dot of light lost among billions of others, and wonder if anyone lives here, if anyone is looking back. This is the interconnectedness of the galaxy, the slow exchange of material across light years, the patient mixing of cosmic ingredients as stars are born and die, as planetary systems form and collapse, as debris wanders through the void carrying memories of places long gone. 3i Atlas is part of that exchange, one fragment among countless trillions, one messenger in an endless conversation written in ice and rock, and we are part of it too. We who build telescopes and write equations and try to make sense of photons that traveled millions of miles to reach our instruments. We who wonder about our origins and our futures. We who look at the sky and ask questions that might never be answered in our lifetimes. We are made of the same material as 3i Atlas, the same carbon atoms forged in stellar cores, the same oxygen created in supernova explosions, the same hydrogen left over from the Big Bang. We are all star stuff, as Carl Sagan famously said, rearranged into different forms, temporary patterns of complexity in a universe trending toward simplicity, consciousness emerging from chemistry, curiosity arising from matter. 3i Atlas doesn't know it's being studied. It has no awareness of the telescopes tracking its motion, the scientists analyzing its composition, the questions it's raising. It simply is. A chunk of frozen carbon dioxide traveling through space, following the laws of physics, responding to the pull of gravity and the push of solar radiation. No purpose, no intent, no meaning beyond what we project onto it. But meaning is what we do. We are meaning makers. We take raw data, photons and spectra and orbital calculations, and we weave stories from them. Stories about distant worlds and ancient stars. Stories about how the universe works and what our place in it might be. Stories that connect the past to the present to the future. And in those stories, objects like 3I Atlas become more than just chunks of ice. They become windows into realms we can never visit. Teachers from whom we learn about cosmic diversity. Proof that the universe is larger and stranger than any single solar system can reveal. The December observations are complete now. The telescopes have been turned to other targets. The data is being archived, processed, analyzed. Graduate students are writing code to model the comet's composition. Postdocs are preparing papers for submission to academic journals. Senior scientists are debating interpretations at conferences and in email threads. The machinery of science grinds forward, slow and methodical, turning observations into understanding. But some questions won't be answered quickly. Maybe not for years, maybe not for decades. What exactly was the carbon dioxide to water ratio? Different instruments measured different values. Reconciling those measurements requires careful calibration and error analysis. Where precisely did 3I Atlas originate? The trajectory can be traced backward, but uncertainties accumulate over millions of years. Narrowing the origin to a specific region of the galaxy requires data we don't yet have. What caused the unusual chemistry? Was it formation environment, or weathering during interstellar travel, or some combination of both? Without ground truth, without being able to physically sample the comet's interior, we can only infer. We can build models, we can test hypotheses against observations, but definitive proof remains elusive. Science is often like this, not dramatic eureka moments, but gradual refinement of ideas, slow convergence toward truth through accumulation of evidence. It's less exciting than movies suggest, more tedious, more uncertain, but it works. Over time, patterns emerge, contradictions resolve, and understanding grows. For 3I Atlas, that understanding will develop over the coming years as more interstellar objects are discovered, as we build up a statistical sample large enough to distinguish typical from unusual, as models of planetary formation become more sophisticated, incorporating diverse chemical environments and temperature gradients, as we learn to read the stories written in comet chemistry with greater fluency, and maybe, eventually, we'll answer the biggest question of all, the question that underlies every observation, every measurement, every paper published about interstellar visitors. Are we alone? Not just in terms of life, though that matters profoundly, but in terms of our chemical heritage, our planetary architecture, our position in the cosmic landscape. Is the solar system that produced Earth, that allowed life to arise, that enabled intelligence to evolve, is that system common or rare, typical or exceptional? One example among billions of similar systems, or a lucky accident unlikely to be repeated? 3I Atlas can't answer that question by itself. It's one data point, but it's an important one. It tells us that carbon dioxide-rich environments exist around other stars, that not all comets are water-dominated, that the frost line, the temperature gradient, the chemical abundances we observe in our system are not universal, that diversity is real, and if chemistry varies, if composition differs, if planetary formation operates under different conditions in different places, then the outcomes must vary too. Some systems will produce planets like Earth, others won't. Some will have the right ingredients for life, others will be barren, and we won't know which category any given system falls into until we can study it directly. That's the long-term importance of interstellar objects. They're the only samples we can get from other systems without traveling there ourselves. And since interstellar travel remains firmly in the realm of science fiction, likely to remain there for centuries at minimum, interstellar objects are our only window into the diversity of planetary systems beyond our own. They're rare, they're fleeting, they're difficult to study, but they're invaluable. The Vera Rubin Observatory will find more of them. The next generation of space telescopes, currently being designed, will observe them in greater detail. Future missions might even attempt to intercept them. To send a spacecraft to rendezvous with an interstellar visitor while it's passing through our system. To capture close-up images. To sample the surface. To drill into the nucleus and analyze the interior. It's technically feasible. Expensive, yes. Challenging, certainly. But possible. Imagine a spacecraft approaching 3I Atlas, coming alongside, matching its velocity, a 68 km/s dash through the solar system, chasing a target moving faster than any human-made object has ever traveled. The engineering would be formidable. The propulsion requirements are enormous, but the scientific payoff would be immeasurable. Direct sampling of interstellar material, analysis with instruments far more sophisticated than telescopes, answers to questions that can't be resolved from Earth's distance. Such a mission is decades away at minimum. The technology needs refinement, the funding needs securing, the political will needs building, but it will happen eventually. Humanity has always pushed outward, from our continent to others, from Earth to the moon, from the moon toward Mars and the outer planets, and eventually toward the stars themselves. Interstellar objects are the first step, learning to chase them, to catch them, to study them, building the capabilities that will someday carry us beyond the solar system entirely. But that's a story for the future. For now, we have the data from 3I Atlas, the images, the spectra, the measurements, and we have the knowledge that interstellar visitors are real, that they pass through our system regularly if we watch carefully, that they carry information about places we'll never see with our own eyes, and that studying them teaches us about the universe in ways nothing else can. The comet is gone, receding into darkness, its brightness fading with every passing day. Soon, it will be too dim even for the most powerful telescopes. Within a few years, it will be lost entirely, indistinguishable from the countless faint stars that fill the sky, and humanity will move on to the next discovery, the next observation, the next question. But for those who tracked 3I Atlas across the sky, who analyzed its chemistry, who calculated its orbit and debated its origin, the comet will remain memorable. Not because it was extraordinary, though it was unusual. Not because it answered fundamental questions, though it raised important ones. But because it was a visitor, a traveler from impossibly far away. A reminder that the universe is vast and full of wonders, and that we are lucky, incredibly lucky, to be alive in an era when we can observe and study and begin to understand those wonders. July 1st, 2025. The night 3I Atlas was discovered. A routine observation by an automated telescope became something more. A moment when humanity detected something from beyond. Something that didn't belong to our solar system, but passed through it anyway. Something that connected us however briefly, to the cosmic community of stars and worlds and debris that fills the galaxy. And December 19th, 2025, the night of closest approach, when 3I Atlas came as near to Earth as it ever would, when telescopes around the world captured their final detailed observations, when we said goodbye to a visitor we barely knew, who came from somewhere we couldn't identify, who traveled distances we could barely comprehend, and who departed as mysteriously as it arrived. The story of 3I Atlas is complete. Not the analysis that will continue for years, but the observation, the encounter, the brief window when this interstellar traveler passed through our instrument's reach and let us glimpse, however imperfectly, the chemistry of another world. What did we learn? That carbon dioxide dominates some comets in ways we never see in our own system. That interstellar space might weather objects during their journey, altering their surface chemistry. That the galaxy is full of diversity, chemical and compositional and structural. That our solar system is just one example, neither representative nor unique, but simply one data point in a vast statistical distribution. What questions remain? Where exactly did it form? How old is it? Has it visited other star systems before ours? What does its unusual chemistry tell us about planet formation in different environments? Will we find more objects like it? Or is it an outlier even among interstellar visitors? We don't know, not yet, but we will keep looking, keep observing, keep asking questions, because that's what we do. That's what drives science forward. Not certainty, but curiosity. Not answers, but the pursuit of understanding. 3I Atlas came and went, a cosmic blink, a moment in the long history of our observations of the universe. But it mattered. It taught us something. It expanded our knowledge. It reminded us that the cosmos is larger than our solar system, more complex than our models, more surprising than our theories. And somewhere out there right now, another interstellar object is making its way through the galaxy. Another fragment of another world. Another messenger carrying another story. Maybe it will pass through our system next year, maybe in a decade, maybe in a century, but it will come. They always do. And when it arrives, we'll be watching. Telescopes ready, instruments calibrated, questions prepared, because the universe keeps sending messengers, and we keep listening, keep observing, keep trying to read the stories written in starlight and ice. And in that effort, in that endless quest to understand, we find meaning. Not in the objects themselves, which know nothing of meaning, but in our pursuit of knowledge, in our refusal to accept ignorance when understanding is possible, in our willingness to look at a faint smudge of light in a telescope and see not just reflected photons, but a connection to the rest of the galaxy. This is the legacy of 3I Atlas, not just data and papers and measurements, but a reminder that we are part of something larger, that our solar system is connected to others through the slow exchange of material across cosmic distances, that we share a galaxy with countless other worlds, some similar to ours, some radically different, all of them products of the same physical laws operating under different conditions. The visitor has passed, the story continues, and the questions it raised will occupy us for years to come. Where did it come from? What does it tell us about planetary formation? Are carbon dioxide-rich comets common or rare? And most importantly, what will the next interstellar visitor teach us? Because there will be a next one, and another after that, and another. The era of interstellar astronomy has begun, and we are witnesses to its dawn. Thank you 3I Atlas for visiting, for letting us observe you, for teaching us that the universe is stranger and more diverse than we imagined, for reminding us that knowledge comes not from assumptions, but from observations, not from theories alone, but from testing those theories against reality. You came from beyond, you passed through, you departed, but your legacy remains. In the data, in the questions, in the wonder you inspired in those who pointed their telescopes skyward and glimpsed, for just a moment, something from impossibly far away. The cosmos is vast, patient, full of surprises, and we are here to witness it, to study it, to marvel at its complexity and its beauty. 3i Atlas was one surprise among many, one wonder in a universe full of wonders. And for those brief months when it graced our sky, we were fortunate enough to watch, to learn, to grow our understanding just a little bit more. The visitor is gone, but the universe remains, full of mysteries waiting to be solved, full of questions waiting to be asked, full of objects waiting to be discovered. And we will keep looking, because that's what curiosity demands. That's what the cosmos deserves, and that's what makes us human. The need to know, the drive to understand, the refusal to accept that any corner of the universe is beyond our reach if we're patient enough, creative enough, dedicated enough to pursue it. This is the story of 3i Atlas, the interstellar comet that came from beyond, that taught us about diversity in the cosmos, and that reminded us once more that we are all connected, all part of the same galactic community, all sharing the same universe, separated by distance but united by curiosity. And in that unity, in that shared wonder at the cosmos, we find perhaps the deepest meaning of all. The stars are not distant and cold. They are our neighbors, and the objects they send us, the interstellar visitors, are their messengers, carrying stories, offering lessons, connecting worlds across the void. 3i Atlas was one such messenger, and we were here to receive it, to listen, to learn, and to pass that knowledge forward to future generations who will continue the work we've begun. The observation is complete, the analysis continues, and the cosmos waits patiently for us to ask the next question, to point our telescopes at the next target, to discover the next wonder, because they're out there, waiting, and we will find them, one interstellar visitor at a time.